And I have a little thing I'd like to confess. Honestly, I brought in Grant Strem because I've wanted to chat with him for a very, very long time, and I just haven't been able to. We actually went to school together a few years ago at U of C. He was a geologist, I was a geophysicist, and I've had a bit of a difficult time catching up since then. I'm so excited to see him tonight. And I'm so excited to see all the work he's done over the last few years. He's one of the very few reasons why I actually still go to LinkedIn and see his posts, because I find they're extremely insightful and informative. And blissfully free of a lot of politics. I think he's an advocate, but he doesn't delve into the politics, which is wonderful. So I won't go too much into his biography, but I mean, he's done a lot of things in those years since we last went to school. Has been a geologist, an explorationist, has worked for a number of producers, has worked as a reserves evaluator, a research analyst, and of course is now a serial entrepreneur. And so I'd like to welcome Grant Strem, CEO and Chair of Proton Technologies. Love to hear your story and what Proton is up to these days.
Thanks very much, Mark. And I apologize for I was not intentionally avoiding you. I'm happy to be here though, and elaborate on whatever questions and directions you'd like to. I'm just delighted to be here and talk about Proton, talk about hydrogen, talk about the change that's going on in our energy systems, and in particular, how that's relevant to Alberta and Western Canada. The biggest differentiators we have are cost. So we believe we can get to roughly 25 cents per kilogram of hydrogen on a levelized basis. We can do it at a carbon intensity lower than 0, and we can do it without creating new ecological disturbances. So those are, I think, quite meaningful differentiators, all three of them on an environmental basis. Why is everyone talking about hydrogen? Well, I just grabbed this screenshot directly out of the Alberta Hydrogen Roadmap that was released about a week ago. And you see at the top here, let's see, here's my cursor. Actually, I can't see it on my own screen, but anyway, we've got 275 megatons of CO2 roughly. And if we do everything that this report recommends, the transformative scenario will shave 14 megatons per year off of that by 2030. So 276 or 275 minus 14 equals a lot. So we're talking 260 megatons. And if you just take 260 million tons and multiply it by our 2030 carbon tax, which is $170 per ton, is the federal carbon tax, and Justin Trudeau just got reelected, you end up with a $44.5 billion drag on the Alberta economy if we achieve the transformative scenario highlighted in this report. So to me, that's deeply troubling. I'm born and raised in Calgary. I like Alberta. I want it to have robust participation in the future global economy. And I don't believe that taking the highest carbon intensity oil of the world, and it is, and it's not that it's just because it starts as bitumen. So like literally it physically has more carbon than hydrogen by ratio than most oil deposits on the planet. But we burn natural gas in most cases to steam it out of the ground, or we take it out with a truck and shovel and use high temperature fluid types of processes to separate it. All of that is very difficult to do with, well, it's not impossible, but it's difficult to do in a way that's carbon free. So that first part is called scope 1 and 2, and then scope 3 is eventually when that product gets consumed as a energy source, there's what's called scope 3 emissions. Now, scope 3, nobody's really talking about it too much in detail yet, but the easiest way for tax authorities to basically tax. One of the reasons CO2 tax is popular globally is because it's so easy for politicians to, ask their scientist, hey, can you calculate how many tons of CO2? And in most things, a scientist or group of scientists can say, yeah, within 5% or so, stoichiometrically, it's about like this. So it's something that's easy to quantify. It's a simple concept, so it's become an easy tax mechanism. And one of the things that I'm nervous about and foresee is that getting wrapped up in the scope 3 emissions set. So anyway, it's something that I think about, and it's something that I occasionally comment on. And I took this same screenshot and put it on LinkedIn, and just kind of drawing people's attention. $44.5 billion per year just for carbon tax if we achieve our best case transformative scenario. I'm very nervous about how that's going to impact our economy and how industrially competitive Alberta has a chance to be if this is not exceeded quite dramatically as a goal. In general, just as an intro, how this works, air that we're all breathing right now is roughly 20% oxygen and roughly 80% nitrogen. So nitrogen does not easily participate in most chemical reactions, but oxygen really does. It loves to react with all sorts of things and oxidize things, including oil and gas. So when gasoline or diesel is burned in your engine, all that's happening is oxygen from the air is combining with those hydrocarbons to release CO2 and steam. That's, a simplification, but that in a broad sense is what's going on. The same thing can happen in the ground. So if you remove the nitrogen, your engine would explode. The temperature of the reaction and the vigor of the reaction would make any conventional engine that's not designed for pure oxygen would just turn, it could not handle or contain the power released from that reaction, which right now, a lot of that nitrogen carries away some of the heat. It calms down the reaction. But if we're injecting something into the ground and we want it to completely react, nitrogen is not going to completely react. And if we just inject air, pressure builds up because the nitrogen's not going to shrink. It's just going to hang out as a gas, and eventually it'll need a relief valve. So it's very difficult, extremely difficult to make a emissions-free process if air is the input into the oil field. If you strip out the nitrogen and just inject the oxygen, however, when it reacts, you get CO2, carbon monoxide, and steam. Carbon monoxide and steam are the ingredients for something called a chemical reaction called water gas shift, which gives hydrogen and CO2. The CO2, we have a patented way to trigger the acceleration of turning the CO2 into carbonate, so locking it in the ground as solid rock, including within the pore space in the bottom water. And the hydrogen, we can either use a downhole filter that only lets hydrogen through up to the surface, or we can bring all the gases to surface and separate the hydrogen and re-inject the CO2 that's unwanted. When CO2 forms carbonate, it also releases hydrogen, which can be a meaningful source. So if people have extra CO2 that they don't want, and they'd rather avoid a carbon tax, they can give it to us and we will gladly transform it into hydrogen. And the CO2 this carbon will remain trapped in the ground as carbonate. So in a nutshell, that's how the process works. Why is it economically very interesting? So I mentioned earlier that I think that we're the lowest cost hydrogen production process that I've heard of. Well, the second lowest, which today produces 95% of the world's hydrogen, is called steam methane reforming, where constantly there's a purchase of natural gas going on. An oil field is never quite empty. So when people say, oh, I have to abandon this old oil field, it doesn't mean that the oil field ran out of oil. It's just reached an economic limit on production. Maybe the pressures dropped. Maybe they tried something after that where they were injecting water or injecting steam or injecting something else. But in all cases, there's still a meaningful amount of oil and hydrocarbons left behind. So if you buy a late life asset when it's become somebody's abandonment liability, where the government will force them to go abandon this well, there's still a huge amount of fuel. So the fuel can be purchased very inexpensively because it shows up as a liability on the balance sheet of the company that's owning it. So the goal is to get very low cost oil fields, and there are many, many undesirable, economically undesirable oil fields around the world. And obtaining those is relatively straightforward in most cases. And then what's needed is to build an air separation unit, get the oxygen in the ground, and then you can have this new source of hydrogen production. So I mentioned that air is 80% nitrogen. So an air separation unit also gives a stream of pure nitrogen. So you can take some of the hydrogen that you make and some of the nitrogen that you make and combine it on site to make a molecule that has nitrogen and hydrogen called ammonia. And there's a big fertilizer market and petrochemical and even energy fuel market for carbonless energy fuel, which I think is going to be growing somewhat through time. Here's another graph that I took from the Alberta Hydrogen Roadmap. It compared a few different, well, let's say speculative things. There is so far, well, I guess they're not speculative. These are technologies that can work and in some cases have been demonstrated, or they might be theoretical. Not all of these, in fact, most of these I don't think are happening yet in Alberta, but they should be theoretically possible. And so I added us to the graph as well as this little happy face on the far right. This is another map I took from the, or sorry, a graph I took from the Alberta Hydrogen Roadmap. And this one talks about carbon intensity. So if you think about wind and solar, you say, well, that doesn't make any carbon emissions. And you're right, once it's up and running and doing its thing, it is not producing extra carbon emissions during that phase. But if you look at the construction, the cement and steel, the transportation, the construction crews and new roads, new power lines, and the decommissioning, that all has a carbon intensity or a carbon footprint that is more than zero. So if you're trying to get to net zero, it's mathematically impossible if your only options in your toolkit have a carbon intensity more than zero. So having one very powerfully carbon negative option that deployed inside your portfolio with no other changes can get rid of a very, very significant amount of CO2. How much CO2? All the CO2. We can grab enormous amounts of CO2 either from industrial emissions where it gets concentrated, or there's our technologies that are, let's say, getting more and more advanced as the whole world is puzzling out how to improve the cost structure of direct air capture. I think that the lowest cost credible one that I've seen is currently about $200 a ton of CO2 for direct air capture. But I think through mass production and a few other tricks, it's likely, in my opinion, to drop below $50 a ton CO2 from direct air capture within the next 5 years or so. And how does it do that? I think it will. I'm not certain that it will. I'm optimistic that there's a path, and I think I see a couple of paths where it could get there. At that point, it becomes a very, very economically attractive thing to do to make all of our energy and exports, including scope 3. So this 275 does not include our scope 3 emissions as a province, which is significantly, significantly larger, but it could all be done. And in a globe that is setting up carbon border adjustments and paying price premiums for the carbon intensity of products, whether oil or even finished goods like cheeses or fish tanks or whatever. If there's a carbon intensity sticker, kind of like organic food many years ago, people will pay for what they feel is better. How much of a premium? I don't know. It's untested, but I think that it's highly likely to be relevant because it's going to be a punishment tool. It will also be an encouragement tool, and that encouragement can draw a big, big price premium to the point where I think Alberta could make more money sequestering CO2 on a net basis from anywhere in the world, because CO2 pushed up a smokestack somewhere on the far side of the planet. We can pull CO2 out of the air on our side of the planet and put it in the ground here and lock it there as carbonate rock. So this is just more or less I guess, a visual recap of what I've already said. Carbon intensity lower than zero is a very, very important distinction. So getting down below zero, it's hard to underappreciate or overappreciate or overstate how important this concept is. So please think of this carbon intensityometer when you're thinking about hydrogen vectors. So in the case of global carbon taxes, Canada is not the highest. It's one of the highest, but there are higher, like Norway, for example, where by 2030 they'll be paying 200 euros per ton. And announcements just keep getting rolled out and pushed out it feels like an accelerating pace. But even if it's just $170 a ton for the sake of argument, on this graph, it shows what happens to the price of hydrogen. So there's a capital expense to build a steam methane reforming facility. That's the gray hydrogen part. And then there's an operating expense. You have high temperature piping and people checking it and replacing things and valves wearing out and flow meters and the whole shebang. And then the gray bar, the darker gray bar here, is just the purchase of natural gas. And that is something that you can't really get away from. But you can see that it's economically overshadowed by 2030 very dramatically, where carbon dioxide emissions become the primary cost. So people say, oh, well, we'll just do the same, only we'll spend a little more on capital expense and we'll spend a little more on operating expense, grab a lot of the CO2, they're talking maybe 85% of it or something, and jam that in the ground. That's something that, I'm so to be clear, I'm not against green hydrogen. I'm not against blue hydrogen. I'm not against pink hydrogen, which is nuclear to electrolysis. I think these all they're all good things to do. I view sort of the main thing we need to get away from is air pollution. So in that context, I really truly hope and believe that 1 or 2 generations from now, kids learn about cars, or they see one at a museum, like we see steam locomotives at Heritage Park. Some sort of a funny old town village where people drove cars that actually burned oil in the middle of cities, where people had to breathe the fumes from that. Air pollution kills millions of people per year. And to me, blue hydrogen, gray hydrogen, green hydrogen, yes, I said gray hydrogen, I think it's all preferable to continuing to burn oil within the cities where we live and work and breathe. But anyway, back to this. If there is companies who would rather pay us, in this example on the graph, $100 per ton to make their CO2 disappear, the price of hydrogen doesn't matter. We could give it all away and still have a very significantly profitable business. Or should I extrapolate profitable province? Yeah, so anyway, I guess short story is for this slide, carbon dioxide has been injected for some time by a company called Carbfix in Iceland. They have a type of rock that is very reactive with CO2. All geological systems will have some rate and form of CO2 transformation to carbonate. Some are much more amenable than others. And if you have a rock type that is not very amenable and you don't have the appropriate dissolved ions in your water zone, you can inject that, and actually people will want you to, because it's the waste streams that help the most. So if you have desalination brine that's high pH and high salinity, or a steam boiler blowdown, or other highly challenging industrial wastewater streams, those are perfect for reacting with CO2 and turning the CO2 into carbonate rock, which releases extra hydrogen in our reservoirs. One of the very nice things, not the entire technology, but parts of it have been accidentally proven here and there in the past. There's been more than 500 projects in the world that injected air or oxygen enhanced air. And one interesting example from Alberta, Marguerite Lake, BP was doing this in the 80s. And we hired some of these guys who accidentally made significant volumes of hydrogen. And they're quite excited. We think that we'll be wildly economic if we can do a small fraction of what they accidentally did while we're optimizing for hydrogen. So to all the skeptics, go talk to these old guys who work for us for like half an hour, and I'm pretty sure you'll walk away wondering whether you should be a skeptic. This is a picture of the main central processing facility at our site in Saskatchewan. There are many projects all over Western Canada where either they've reached the end of their life or they were never developed because the quality of the oil field was such that it was very hard. There was perhaps no aquifer support, or some initial geological condition made it a tough go as an oil field. But the resource itself might be gigantic and fairly well known about. It's just not drilled or not being produced because of other challenging aspects. Much like Northern Alberta, for most of the last, until let's say 1990, there was only niche stuff going on in mining. For the most part, that's not fair to Imperial, who's been around for a long time doing stuff. Yeah, I think I'll probably flip towards Q&A. So let me stop sharing my screen. And should I start in the chat box? I guess so. Let's see what we got.
Grant, this is Karang. I also have a question, if you don't mind.
Yes, please.
So a question may come to mind that, like, pure oxygen is the core element for the process that you were explaining, if my understanding is correct. So needless to say that the equilibrium has been taken into consideration. If the oxygen is to be extracted from the air, is it carbon? Is it carbon incentive? Is it creating footprint for the carbon as well?
The initial hardware and the tank construction and things like that does have an associated footprint until we start making, clean steel and everything on the whole mining side changes. It's really hard to make a carbon-free steel tank or things like that, or rotary shaft or equipment. So yes, there is a footprint associated with that. At the University of Calgary, one of the master's students, Chris Wolf, did a project for us, a very data heavy project. I think it was about 200 pages, where he went through what is the life cycle carbon intensity of Proton's process, assuming no additional CO2 is added. And we beat wind and solar to electrolysis on carbon intensity. But we're still above zero. We have to grab additional CO2 and jam it in the ground in order to do that. So there is an energy footprint for the, and the reason it's so low is the energy footprint for running the air separation unit comes from a portion of the hydrogen we produce. So if we produce 100 units of hydrogen at a site, we need about 15 units of hydrogen to power a turbine, and the turbine makes the electricity to power the air separation unit. So there's no emissions generated at site, but to get lower than zero, we must grab CO2 from external sources and drag it down with our oxygen.
Thank you.
Yeah.
I mean, I have more questions, but I won't be fair to the rest of the audience, so I'll just wait. Maybe those questions been asked by somebody else.
Having trouble with scrolling too fast in the chat box. Let's see. Given the number of abandoned wells in Alberta, would the AER be highly interested in this? I would say that members of the AER individually are highly interested in this, but as an organization, it's very difficult for changes in policy to be made. And if there's no strong advocates right at the top, it's difficult. And I'll give you an example. And I do hope to grab something out of the Orphan Well Association, just as a, look, we did it. But that's a much more difficult path. If we buy something in a bankruptcy process, it comes with the minerals, it comes with the wells, it comes with the lease with the farmer, it comes with all the things come as a package. But if you take a well from the Orphan Well Association, you get an old well. So you have to separately go find, a deal with the farmer. You have to separately go consult with the natives. You have to separately go do all the different pieces. You have to bid on the mineral rights and go do the whole thing from square one. So it does make it a less attractive path in that way. So I would suggest an improvement could be for the Orphan Well Association to be able to do more of this type of thing. There must be an option to leave some of those agreements attached to the well. It'd be otherwise it's just easier to go get a different project. But I agree, they should be highly interested in this. So can you comment on investments in hydrogen distribution and combustion technology for energy creation? Yeah, there's been massive investments worldwide. There's many combustion technologies. We're planning to order recips for our site in Saskatchewan for powering the electrical grid for Sask Power. We have a 20-year PPA. But there are several recips you can buy, but there are also several turbine options you can buy. And it mostly has to do with, and there's often retrofits available. So you need an injector plate that can handle higher temperatures. Sometimes you need larger diameter supply pipes right at near it. And in some cases, if NOx, nitrous oxides, are a challenge, then you need to have either a mist or a steam system that basically takes some of the, you can use exhaust heat and make some steam and breathe it in right at the front end, and that subdues the overall temperature. So, and it also increases the flame length. So there's been, I don't know if they're advances. This is stuff that, in the 1940s, the V2 rocket engineers probably had mathematically figured out, but now it's in broad industrial application, and it's not like secret knowledge or anything how hydrogen combusts. And in terms of transportation, I think the biggest secret is if you can make hydrogen cheaper than natural gas, power lines are the easiest transportation path. So you can put gigawatts and gigawatts into the grid. Everybody's switching to electric cars, and people are saying, there's not enough room for solar panels in our beautiful place and not in my backyard and all this. Fine, just get the hydrogen from one of these sites, cheaper than natural gas, and make electricity, perhaps right at that same site. But if you want to move pure hydrogen around, you're kind of looking at three main paths. You compress it, which there has been improvements to the carbon overwrapped pressure vessels that allow you to put higher pressures in the tanks, which means more kilograms of hydrogen per load. But that's usually still relatively short haul scenarios and not high volume scenarios. You can liquefy it. That's better. You get about 10 times more on a truck as a liquid. And to give you a sense of scale, we think it'll be about $3 a kilogram from our field site in Saskatchewan to San Francisco as a liquid. And they're selling it for, clean hydrogen goes in San Francisco for like $12 US or something. So the arbitrage possibilities if you liquefy hydrogen are pretty significant. And then the other way is in pipelines. So pipelines that can handle high H2S are generally already compatible, but there's not so many of those pipelines around. And it's actually not legal yet to put large volumes of hydrogen or even small modest volumes blending into distribution pipelines. And the big challenge here that I don't see a solution to, and we started talking with Alberta politicians about this like 2 years ago, almost to the day. And it wasn't just me, there was a bunch of big pipeline companies in the room. We were saying, please make the regulations so that we can put some hydrogen in the pipes. Maybe it's 1%, maybe it's 2%, but give us something. And the challenge is, if you put something into the main distribution grids, unless it's a one-way pipe, you don't know if that molecule of hydrogen ends up in Chicago, California, Edmonton. Like, where's it going to get used? No one really knows. It's just the gas pipeline. So until all of the regulators, more or less, most of the regulatory bodies in North America all agree together on a standard, and maybe it's just 1%, and I really wish they would all agree on that, and I wish there was an advocate for it. But until that happens, you're just not allowed, which to me is, you have this huge infrastructure that could probably handle, well, to give you a sense of scale, 5% of the US gas supply is 30,000 tons per day of hydrogen, which is quite a bit. So yeah, that's 30 million kilograms per day is 5% of the US gas supply if you blend it in hydrogen. So yeah, those are the main ways to move pure hydrogen. You can blend it in. There are pure hydrogen pipes. There's several ways to get hydrogen back out at the destination, usually involving membranes. But yeah, that's there are other chemical paths if desired. You can make ammonia, you can make methanol, you can make these other things, but those are the main ones. Can you produce enough hydrogen to power a grid scale generator that has installed hydrogen ready turbines, and are there opportunities for a co-site installation? Great question, Rob Miller. Yes, so we plan to do this exact thing. We've got one customer who's hoping for 400 megawatts from us on site, a data center customer. And one of the nice things about data centers is they like cooling, and we have a whole bunch of cryogenic fluids that we're trying to warm back up. So it fits really well for that. And in terms of the grid, yeah, that is our main target. We're hoping to do a couple gigawatts in Texas. There's a whole bunch of stuff. A deregulated electricity market is good, but so far our PPA is with Sask Power, and that's the first one we'll have probably online about 1 year from now. Let's see. Hi, Grant. I can see where the value add is a bolt-on for heavy oil. I come from a CBM, coal bed methane background, Colin McDonald, and I was wondering if anyone is looking at the parallels of syngas production, H2 extraction from in-situ combustion of deep coal seams. Yes, I've spent a lot of time personally thinking about this, looking at this, and my conclusion is that Proton will never do a project that involves a coal deposit for, I guess, call it three main reasons, maybe there's four. The first is that in an oil field, usually 2/3 or more of what's in an oil field is rock. That rock framework is constantly stealing heat. So you're heating up rock grains according to the specific heat capacity of that rock. And in a coal seam, it's all fuel. So the temperatures can get far, far higher within a coal to the point that you can actually have thermal decomposition of water molecules where if you're talking lower temperature things, the oxygen gets locked, attached to carbon, or locked, attached to something else. But if you break water at high temperature, that oxygen, some of it will end up reacting with coal. And in that way, you can end up with a self-perpetuating runaway reaction. And there are examples of this around the world. The risk of that is not just high. If you have an unknown water leg in a coal, it's like almost a certainty in many conditions. So we don't plan to dabble at all in that. The other thing is when you consume all the oil or all the hydrocarbons from an oil field, you still have that rock framework there to hold up the roof. In a coal seam, you don't. There will be subsidence. If you've got 10 meters of coal seam in the subsurface that you use up, the land on top will drop approximately 10 meters in the course of time. So that reactivates old faults. It basically causes wellbore shear off, technical risk, and there's a pretty high chance that you'll disturb the overburden in such a way that you might find some of these hot gases or unwanted gases finding a path to surface. The third reason is essentially perception. So even if we could make a huge amount of money and think we could safely do it, I think that there are, just because there are real risks and real bad examples in coal. Yeah, even if we felt we had a perfect technical solution, I don't think we'd do it just because everyone would be nervous. Regulators would and could and should be nervous. The level of scrutiny for everything would be so much higher, and it's not necessary. The world has a whole bunch of oil and gas deposits that work well. Have you studied how will the process work in high temperatures, such as thermal oil sands operations? They're perfect. So they're preheated, they're soggy, full of steam. Yeah, they're all the wells are thermally cemented already. There's an approval in place. Some government people and company people have already looked at the cap rock integrity and assigned a maximum operating pressure. You know, there are many aspects that make post-thermal more attractive than, in my opinion, other things we've been looking at. Guess we'll have to go to audience questions now. Is there like a hand raising option, or how do we do that?
I mean, audience can actually unmute themselves, if I'm not mistaken, and then ask questions.
Jesus Jayero, IPO question mark. I'm not sure what I can and can't say, so I won't. Sorry.
Jesus, if you could elaborate on the IPO question mark.
I think it's a question about Proton going public. And so I think Grant has skillfully answered the question.
All right, okay.
So Grant, it's, your background is, geoscience, and this process is all, chemistry focused, engineering focused. How has your journey been so far?
I'd say mostly painful. So, yeah, trying to break it down and simplify it. Like, it's really easy. You probably saw in my Q&A, I probably get a little too technical for an average crowd of investment bankers. It's painful for them and it's painful for me. So how can I just, what are the key points here? And I try and distill it as much as I can. One of the main things I can focus on is cost. And I think for me, the journey has been learning to better simplify the message, and yeah, finding patience on the way to the next milestones. So I think I'm somebody who really wants to go a lot faster than reality permits, and that's been a struggle as well. And especially the probably the hardest challenge historically had been access to funds. So I would talk about this to somebody, even somebody who understood it, and I just could not understand why, if they believe it's transformative, the downside, we're covered because we've got an oil field that's worth this, and the PPA with Sask Power, and it's attractive for these reasons. Even if the hydrogen doesn't work, this investment is not bad. And yeah, I just don't know. I want to see it bigger scale first. So trying to get to the next milestone and the next scale, to me, has been a painful distraction. It's not what I like to do, and it's not my primary. It's not primarily how I think I like to think about challenges. Of course, it's part of the equation, and it's an important one. So how are we optimizing our use of steel, or how do we buy oil fields for less, or are there energy or other ways that we can better integrate this equipment to save money, because greater efficiency is also greater for the environment, and the lower cost means the technology can proliferate more quickly. So it's a design challenge that's financial in large regard, but actually trying to get people to write checks as investors or lenders or whatever has been, for me, the most painful part of the process. That said, the journey has also been great in several ways. I've been encouraged, I should say, on the flip side, by the rare person who does say, wow, this is so cool, and I want a better Alberta future too. And I'm an accredited investor. Here's $10,000, and then we can, it all sort of adds up to help take us to the next step, whether it's small or large. Lately, we've brought in a bunch of larger shareholders, which has been very helpful. But yeah, I think there's little joys throughout. I like the people that I work with. I think the team is they're excellent and poised to build an air separation unit and collect the right kinds of data and look at it hopefully the right kinds of ways. And it'll be an iterative process for the first few as we learn how to improve that. And so I'm excited about where we are as a team, and against the backdrop of a decarbonizing world that has a lot of, I guess, attractive headlines around hydrogen, it's making our job a little bit easier, and I can think more about what we're going to build and who's going to build it, and schedules, and those kind of aspects are probably a more useful way for me to spend my time than financial engineering, although that has necessarily become part of my hard knocks education. So was that a good enough answer?
Oh yeah, thank you very much, Grant.
And
It's almost the same thing with almost every volume technology, right? So you guys are on a journey, I guess. Yeah, it's great. Yeah,
in
the
terms
potential
of,
is huge, right? Like everybody who looks at your posts on LinkedIn, he definitely wants to read it.
Well, thanks. Yeah, I think this could be a massive provider of energy for the whole world, or an energy trajectory that has not been implemented before. So at this cost structure, at the end of the day, that's what will make things proliferate, is it cheap. And it just happens to be cheap because it takes advantage of so much existing investment and infrastructure that's been built out over the last century. So that whole body of knowledge, I think, is culminated in a fairly simple step. Why oxidize on surface? We don't want air pollution. We don't want CO2. We can keep all that stuff in the ground and, turn these oil fields and gas fields into reaction vessels that store the CO2 as rock. It's not like a huge leap beyond what's been done, but I'm trying to proliferate this technology. So the time has come to do it.
So just a general question, Grant, with respect to bringing the H2 as a fuel source for example, generating electricity and in the scale. And then is it like, how does it work? Is it like, maybe I'm just using an analogy. So comparing shale gas fields compared to conventional. So shale gas wells are short-lived. So you have a limited amount of production out of them, and then you have to go for another one. How does the sustainability of production for the hydrogen using your technology pan out?
Well, sustainability is basically until the fuel supply is gone and the pore space is more or less full of carbonate. So, and even then you've got this very hot rock volume that can spin geothermal turbines for another few decades, even, at the end of life. So, if you think about from an efficiency standpoint, there is more fuel per cubic meter in an oil sands deposit because the porosity might be 35% than there would be in a shale gas deposit where the porosity might be 5%. That said, many of the shale gas projects being developed have organic content within the rock framework itself. So if you have 2 to 5% TOC, or just even 2 or 3% TOC, if you look up how much oxygen reactive material that is within that cubic meter, that is a significant fuel source also. So it might be a good depleted gas well from a storage perspective, because as I mentioned, if you get CO2 to transform into carbonate, that releases extra hydrogen. But there's also the cheapest way to get that CO2 in the ground is by dragging it down with this expanding oxygen. So you have a fuel supply in the rock itself, often within shale gas. But all of those advantages and interesting points with a gas play are things that we'll be quantifying through time. So the relative efficiency, there might be some surprise factors. In the back of my mind, I know that most shale gas plays are higher pressure naturally. So if you end up, if the virgin reservoir pressure was 20,000 kPa, the steam temperature will be much, much higher. The temperatures you can get to within the Goldilocks zone of water gas shift, that might be something that's easier to constrain and contain more efficiently. So there will be, if you're building a big air separation unit somewhere, and there are other zones, like definitely it's crazy not to divert some of that oxygen to test other geological concepts at the same time. And there will be, I think, some positive and negative surprises as we quantify them all.
Absolutely. This is a very interesting topic, and I'm sure everybody's is also so excited to learn and hear more about it. But the time also has limits for us, so we're just getting close to the top of the hour. Your time is valuable, Grant, so we don't want to hold you for too long. Is there anything that you wish to share with us before we actually end the session for today?
Yeah, there's a few thoughts swimming around, but if I had to just pick one to talk about right now, I would address the other oil and gas companies in Canada who are facing the same carbon tax burden as companies. And it's not just a government problem. Most oil and gas companies have very large internal carbon intensity footprints. I would highly encourage you to look into either a license deal with Proton, and we will be very, very happy and generously helping to implement this and proliferate the technology within our roof or under yours. And the other thing is, even more interesting for us, because it might be a faster path, is an offtake agreement. So, Whitecap Resources signed a license with us. There are others who have signed licenses with us. But an offtake deal does not require a super deep evaluation for 2 years on our technology. If we can sell you hydrogen cheaper than you can buy natural gas, and we can, and we will, please consider signing an offtake deal for hydrogen from us, and we'll build something very large scale in your neighborhood.